Okay, let's start with the first problem. Let f of x be defined by this function. Find all critical points of f. Classify each critical point as a local max, local min, or saddle point. Compute the value of f at each critical point. First of all, notice that we're looking for local max, local min, or saddle points. So this is not global extrema. This is local, which means we're using the first derivative tests, and we're not using Lagrange multipliers. So how does this work? We're going to take the first partial derivatives of our function and set them equal to 0. A quicker way to think about that is just taking the gradient of f and setting it equal to the 0 vector. Same thing. So let's do that. Partial of f with respect to x is 3x squared plus 6x. And we're going to set that equal to 0. The partial of f with respect to y is 3y squared minus 12. And we're going to set that equal to 0. Okay, so our job now is to solve both of these equations simultaneously. Starting with the second, which looks a little bit easier. So this implies 3y squared equals 12, which implies y squared equals 4, and y equals plus or minus 2. Now let's go to the other one. This one has a little bit of factoring, so we're going to factor out 3x times x plus 2. And this implies, of course, that x equals 0 and x equals negative 2. So we have a few combinations here. We have x is 0 and y is negative 2. X is 0, y is positive 2. X is negative 2, y is negative 2. X is negative 2, y is positive 2. Okay, so these are our 4 critical points. We're going to have to test each of them and classify each one. So let's calculate next the discriminant. So remember, the discriminant is a function of x and y. And it's defined by the second partial with respect to x times the second partial with respect to y. And we're going to subtract the mixed partial derivative squared. Let's go through and calculate that here. The second partial derivative with respect to x is 6x plus 6. Second partial derivative with respect to y is 6y. The second, or the mixed partial derivative, you can use either one. If we take the derivative of fx with respect to y, see that there's no y's showing up, so this is just going to be 0 squared. So now we can evaluate the discriminant at each critical point, one by one. So the discriminant at 0, negative 2 is 6 times 0 plus 6 times 6 times negative 2. And that gives us negative 72. Discriminant at 0, positive 2 is 6 times 0 plus 6 times 6 times 2. This is going to give us positive 72. Discriminant at negative 2 is 6 times negative 2 plus 6 times 6 times negative 2, which gives us negative 12 plus 6 is negative 6 times negative 12, positive 72. Discriminant at negative 2, positive 2 is 6 times negative 2 plus 6 times 6 times positive 2, which gives us negative 72. It's a bit tedious, but you have to do that for every single one. Now we like these two cases, the negative numbers. Whenever the discriminant is negative, you automatically have a saddle point, and you're done with that critical number. So that's our favorite case. The second two, we have to do a little bit more work. So we also have to take the second partial derivative with respect to x, which we had up here, 6x plus 6. And we're going to evaluate it at each of our remaining critical numbers, 0, 2. And we get positive 6, which is a positive number. Now, when you have the discriminant positive and the second derivative with respect to x positive, this implies a minimum, a local minimum. Now let's take the second derivative with respect to x and evaluate it at the second critical number where we had a positive discriminant, which is 6 times negative 2 plus 6, which was negative 6, so a negative number. When you have a discriminant positive and a negative second derivative with respect to x, this implies a local max. Okay, so we classified all 4 critical points. The last part of the problem just wants you to find the output at each critical point, and that's just plugging in and calculating f of 0, negative 2, f of 0, positive 2, f of negative 2, negative 2, and f of negative 2, positive 2. And that's just plugging into the original function here and seeing what you get out. Okay. The second problem. Find an equation for the tangent plane to the surface z equals f of xy as defined by this function at the point where x equals 3 and y equals negative 1. So we would just have to remember the formula for the tangent plane. Very basic problem if you just remember the formula. Remember that the tangent plane is the same as, it's going to be used for a linear approximation, so we'll write it as such. Linearization at x comma y is equal to f of x naught y naught plus partial x evaluated at x naught y naught times x minus x naught plus partial y evaluated at x naught y naught times y minus y naught. Okay, and this is going to be linearization at the point x naught, y naught, f of x naught, y naught. Remember that this is just a fancy name for z naught. You have x naught, y naught, and then your output is z naught. So it looks like there's a lot to this formula, but there's really not. This is just, again, this is the original z. And you can get that by plugging in x equals 3 and y equals -1 into the original problem. So let's do that. F of 3, -1 equals 3 squared plus -1 cubed plus 3 times -1 plus 21. Simplifies to 9 minus 1 minus 3 plus 21. And we're going to get 30 minus 4, 26. This number here is 26. Okay, now we're going to need the partial derivative evaluated at that point. So let's find that. If x is 2x plus y, we're going to evaluate it at the same point, 3, -1, which is 2 times 3 plus -1, which is 5. Now let's do fy at that same point. So we're going to get 3y squared plus x. We're going to evaluate that at the same point, and we'll get 3 times -1 squared plus 3. So this is just 3 plus 3, which is 6. So we've got this number now, and this number. Let's go through and write that. Our linearization xy is equal to 26 plus 5 times x minus, and remember, x naught, y naught, z naught. So our point is 3, -1, 26. So x naught is 3 plus 6 times y minus -1, minus -1, which is plus 1. So that's our answer to part A. Now notice that this is exact for the point 3, -1, 26. If you plug in x equals 3, this term would become 0. You plug in y equals -1, this term would be 0, and you would get out 26. Linearizations are exact at the point at which you build them. But now for part B, we're going to use the linearization to approximate f of this new point. F of 3.1, comma, -1.2. This is going to be approximately our linearization at 3.1, -1.2. Now this only works because these 2 points, these 2 numbers are very close to the original point we had, x being 3 and y being -1. So we're allowed to use this linearization to approximate it and get a pretty decent approximation. And you won't have a calculator on your test, but that's okay, we can do it in our head. 5 times 3.1 minus 3 plus 6 times -1.2 plus 1. Simplify this a bit. 26 plus 5 times 0.1 plus 6 times negative 0.2. 26 plus, this is 5 times, this is 0.5. And 6 times negative 0.2 is negative 1.2. So this comes out to 25.3. So let's see what we get if we take this point and plug it directly into the function, assuming that we had a calculator on our test. I'm plugging the wrong number. 3.1 squared plus negative 1.2 cubed plus 3.1 times negative 1.2 plus 21. The actual answer that we get is 25.162. So you see our linearization is pretty close to the actual answer. And that's all for problem 2. Okay, problem 3. Find the global maximum and minimum values of f of x, y, as defined by this function, on this domain xy, all xy such that x squared plus y squared is less than or equal to 4. So it's a good idea to start by graphing our domain and seeing what we're working with. It doesn't have to be perfect, just a real quick sketch. You should recognize this as the equation for a circle of radius 2. Not a perfect picture, but okay, and this means all the points on the boundary and inside the circle can be considered. So we're going to do this problem 2 different ways. First, we're going to try it with the parameterization of the boundary. And the second way, we're going to try it with Lagrange multipliers. So the first step on this problem is to consider all the points on the interior of the circle. That's the same as the first problem, just using the first derivative test. So we're going to take the gradient of f and set it equal to the 0 vector. Again, what this just means is taking the first partials and setting them equal to 0. So fx is equal to 2 minus 2x. Fy is equal to negative 2y. And again, we're going to set these both equal to 0. Well, this one's really easy. This gives us y equals 0. And the first one gives us x equals 1. So our critical point on the interior is 1, 0. That's the only point on the interior that we have to consider. Now we should always make sure that this point is actually in our domain. So if you can't see it immediately that the point is right here, you can plug into the inequality and make sure you get something true. 1 squared plus 0 squared less than or equal to 4. Well, clearly 1 is less than or equal to 4. So this point is in our domain. Now we don't care about if this is local min or a local max or a saddle point anymore, because they're asking us to find the global maximum and minimum values. So we're just finding all the possible points, and we're going to test their z-values and pick the biggest and pick the smallest as their global max and min. Okay, so here's where we're going to split into two different techniques. We tested the interior of our region. Now we have to test the boundary, which is a little bit difficult to do when you have a circle. So what we're going to do first is parameterize the circle. Remember how to parameterize a circle from earlier in the course. We're going to let x be the radius, in this case 2, times cosine t, and let y be the radius times sine t. Now if we do that, our equation instead becomes a single variable equation. Ten plus 2, and our x now is 2 cosine theta, or cosine t, excuse me, minus 2 cosine t squared minus 2 sine t squared. So we'll simplify this a bit. 4 cosine t minus 4 cosine squared of t minus 4 sine squared of t. Ten plus 4 cosine t. Now if we factor out minus 4 from both of these terms, we'll get minus 4, and then cosine squared plus sine squared, which is identically just 1. And so our equation becomes real nice. 6 plus 4 cosine t. Okay, so now this is a single variable maximization problem, 20A problem at this point. We'll take the derivative. Derivative of cosine is negative sine, so this is negative 4 sine of t. We'll set this equal to 0. Well, this means t is equal to 0 and t is equal to pi. These are two spots where we'll have horizontal tangent lines. Okay, now when t equals 0, if you look back at our parameterization, this means that x equals 2 times cosine of 0. Cosine of 0 is 1, so x equals 2. When t equals 0, y equals 2 times sine of 0. Sine of 0 is 0, so we get y equals 0. Now when t equals pi, we'll have x equals 2 times cosine pi, which is negative 2, and y equals 2 times sine pi, which is still 0. Now we didn't have to consider t equals 2 pi, because that's the same angle as 0. Our critical points are 1, 0, 2, 0, and negative 2, 0. Now we'll just plug them into the original problem and see which has the biggest output and the smallest. Okay. F of 1, 0 is 10 plus 2 times 1 minus 1 squared minus 0 squared, which is 12. F of 2, 0 is 10 plus 2 times 2 minus 2 squared minus 0 squared, which is equal to 10 plus 4, 14, minus 4, which is 10. F of negative 2, 0, we get 10 plus 2 times negative 2 minus negative 2 squared minus 0 squared. So this is 10 minus 4 minus 4, which is equal to 2. So our global max is 1, 0, 12. Our global min is negative 2, 0, 2. So that's our first method. Now let's try it a different way. Let's stick with our first critical point that we found, because that part won't change. 1, 0 is our first one. Now let's test the boundary region of our domain using Lagrange multipliers, because we're trying to maximize or minimize this function here, subject to the constraint that x squared plus y squared is equal to 4. Now we're ignoring the inequality because we already found the critical numbers on the interior. So now we're just worrying about points that are on the boundary. So let's set up the method of Lagrange multipliers. We'll take the gradient of f and set this equal to lambda times the gradient of our constraint function. Excuse me. Constraint function. Xy was 10 plus 2x minus x squared minus y squared. And our constraint was x squared plus y squared equals 4. Now the way you find your constraint function is you move all the terms onto one side of the equation. And you just set your constraint equal to that. So this is f, this is g. We can set up the vector equation. So we'll take the gradient of f. We'll have 2 minus 2x for the x component, and the I component, excuse me, and negative 2y the j component. We'll set this equal to lambda times the gradient of the constraint. Gradient of the constraint is 2x, the I component, and 2y for the j component. Now, two vectors are equal if and only if their components match. So that means that 2 minus 2x has to be equal to lambda times 2x, setting the I components equal. It also means negative 2y has to be equal to lambda times 2y. And the last equation is just your constraint. X squared plus y squared equals 4. So we're solving a system of equations here with 3 variables and 3 equations. The unfortunate part is that there's not a surefire way to always solve these equations, so you have to use a little bit of intuition. Typically what you'll do to start though is to solve the first 2 equations for lambda and set them equal. So let's see what happens if we try that, starting with this one. Negative 2y equals lambda times 2y. So it's very easy to divide both sides here by 2y. But if we divide both sides by 2y, we have to consider the case that y could be 0. So let's see if it's possible for x to be 0, y to be 0, or both to be 0. So let's first start with x being 0 and y not being 0. Now if x is 0, the first equation becomes 2 minus 0 equals 0. And that is not a true equation. That is not a true statement. So this case is not possible. We'll be looking for false statements like that to decide which cases we have to throw out. Now let's say x is not 0 and y is 0. Well, in that case, if y is 0, the second equation becomes 0 equals 0, which really tells us nothing. The first equation tells us nothing because it does not have y in it. And if we plug y equals 0 into the third equation, we get x squared plus 0 equals 4, which implies x equals plus or minus 2. So we do get a few critical points. Actually, these are not critical points, but we do get a few test cases. 2, 0, and negative 2, 0 that we'll have to check later on. And then finally, the case where x equals 0 and y equals 0, well, that's not possible, because if you look at the third equation, it would become 0 equals 4, which is clearly false. So that takes care of these 3 edge cases. Now let's go back to our original equation here. If we look at this equation, we get dividing by 2y. We're allowed to do that now that we've ruled out these cases where any of the variables are 0. This implies that lambda equals negative 1. Now, oftentimes you don't ever actually find out what lambda is. In a few problems you will, like this one. So let's take this lambda and plug it back into the first equation to try to solve for x. So we'll get 2 minus 2 times x equals negative 1 times 2x. Well, notice we have negative 2x on both sides of the equation. So if we cancel these, we get 2 equals 0. Now we haven't done anything wrong. It just means that we don't have any more points that could be maxes or mins. We have our original point 1, 0, the 2 points that we just found. And again, we would plug all 3 of these into the original function and see which gets the largest z-value and the smallest z-value. Now, if we did this correctly, these should be the same 2 points we found using the first strategy. 1, 0, 2, 0, negative 2, 0. 0, 2, 0, negative 2, 0. So both techniques will work, whichever way you're more comfortable with. Will get you the correct answer. Question 4. Light is turned on near the lair of a wolf spider. The brightness of the light is given by this function b of x equals 18 over 1 plus x squared plus y squared lumens with x and y in centimeters. To get away from the light, the spider crawls along a path r of t, so that, now notice r of t is a vector function, so that 2 seconds later its position is r of 2 equals 2, 2, and its velocity is r prime of 2 equals 7, 5. The rate of change of brightness in lumens per second along the spider's path as time equals 2. There's a lot going on in this problem. Let's break it down a little bit. B is in lumens. And the problem is asking us to find the rate of change of brightness in lumens per second. So that gives us a key that we should be finding lumens per second for dB dt. Now, if you look at your b of x, y function, it has no t's in it. So x and y are functions of t. So this is a chain rule. This is a multivariable chain rule problem. Let's set up the tree. B is a function of x and y. X and y are both functions of t. So this derivative will be equal to partial b with respect to x times derivative of x with respect to t plus the partial of b with respect to y times dy dt. Now, partial b with respect to x and partial b with respect to y we can find from the given equation. Dx dt and dy dt we cannot, because we don't have explicit formulas for x of t and y of t. But that's okay, because we have an r of t function. So remember that r of t is a vector function that contains the parameterized x and y functions, so x is a function of t and y is a function of t. What that means is that r of 2 equals x of 2 and y of 2. Now they told us this equals, in this particular problem, this equals 2, 2. So from this we can gather that x of 2 equals 2 and y of 2 equals 2. Now furthermore, they told us r of t, or r prime of t, excuse me, equals, well, let's take a step back. So r prime of t is just going to be equal to x prime of t for the I component, and y prime of t for the j component. But that means that r prime of 2 is equal to x prime of 2, y prime of 2. And in this particular problem, they told us the velocity vector is 7, 5. So this means x prime of 2 equals 7, and y prime of 2 equals 5. Now we're going to need these data later on. So we're trying to find dB/dt, which is going to be given by this formula. We don't need an explicit formula, we just need to know dB/dt. At time equals 2, which means that we have to evaluate this quantity at time equals 2. Now notice that when time equals 2, that means x equals 2 and y equals 2. Now it's just a coincidence that they're all the same numbers. It could be the case that x of 2 was 3 or y of 2 was negative 5. But in this case, they're all 2. So let's go through and calculate partial b with respect to x. And we're going to rewrite our formula as 1 plus x squared plus y squared to the negative 1. We're doing this so that we can avoid the quotient rule. And now let's calculate partial b with respect to x. Negative 18 times 1 plus x squared plus y squared to the negative 2 times the partial derivative of the inside, which is 2x, and the partial derivative with respect to y is negative 18, 1 plus x squared plus y squared times 2y. So evaluating partial x and partial y at time equals 2 is the same thing as evaluating them at x equals 2, y equals 2. Again, because time equals 2 corresponds to x being 2 and y being 2. Okay. So notice that we're plugging in 2 for every x and y, so the numbers should be the same on both of these. So negative 18 times 1 plus 2 squared is 4, plus 2 squared is 4, to the negative 2, times 2 times 2 is 4. This is equal to negative 18 times 9 to the negative 2 times 4, which is equal to negative 18 over 9 squared times 4, which is equal to negative 18. Well, negative 18 is 9 times 2, so we'll write this as negative 9 times 2 times 4 on top over 9 squared, which is equal to negative 2 times 4 over 9, just canceling out one of these 9's, and we get negative 8 over 9. So dB dt evaluated at time equals 2 is, again, dB for partial b, partial x times dx dt plus partial b with respect to y times dy dt. So we just found these two numbers to be negative 8/9 and we want dx dt and dy dt, but we never had x and y as explicit functions. We do, however, have x prime evaluated at 2, which is 7, and y prime evaluated at 2, which is 5. So we're going to plug those numbers in for dx dt, dy dt. Okay, so this is 13 times negative 8 over 9, which turns out to be negative 104 over 9 lumens per second.